All right, today we're going to put on our detective hats for a bit of a scientific mystery. Seriously, this is a case where the main clue is smaller than a wavelength of light. And the culprit? Well, it might just change how we build, well, everything for the future. We're calling this one the case of the flawless flaw. So just imagine for a second the nose cone of a hypersonic jet or maybe a spacecraft just blasting back into the atmosphere. The temperatures are, they're absolutely brutal, right? To survive that, you need these super special materials. They're called ultra-high temperature ceramics, and they have one job: take that incredible heat without failing. The bottom line is, the stronger we can make them, the further and the faster we can go.
But here's the twist. What if the secret to making these things stronger is actually a tiny, perfect flaw? I know, it sounds completely backward, doesn't it? Because in material science, a flaw, an impurity, any kind of imperfection, that's usually bad news. It's the starting point for a crack, for a catastrophic failure. But what if a certain kind of flaw was actually a feature, not a bug? That's the huge paradox we're diving into today.
Okay, so to solve this thing, we've got to get to know our main subject a little better. Let's talk about these materials, the ones built for the most extreme environments you can possibly imagine. So the material right at the heart of our case is called zirconium diboride, or just ZrB2 for short. And this stuff is a total superstar in the world of ceramics. It's known for its absolutely incredible heat resistance. And scientists, they were just trying to make it even better, mixing it with stuff like graphite, when they stumbled onto something kind of odd. And that's the key right there. This wasn't a planned discovery at all. It was just an anomaly, a tiny little detail that just didn't quite make sense. And it's so often these totally unexpected moments that end up leading to the biggest breakthroughs. So deep inside these otherwise perfect crystals of ZrB2, researchers spotted these little tiny pockets. The technical term is inclusions. And when I say tiny, I really mean it. We're talking about 250 nanometers across. Now, to put that in perspective for you, a single human hair is about 80,000 nanometers wide. So yeah, these things are just unbelievably small. Okay, so normally, an impurity like this, it's like a tiny pebble that got baked into a loaf of bread, right? It's going to warp and stress everything around it, creating weak points. That's what should happen. But when the scientists looked, the area around these little inclusions was just perfectly calm. There was this remarkable absence of the strain they totally expected to see. It was, for all intents and purposes, a flawless flaw. So how is that even possible? That's the question that just baffled the researchers. How can you have an imperfection that creates absolutely no stress? It pretty much defies the rules of material science. So it was time to bring in the high-tech forensic tools. Right. To crack this case, our science detectives needed to get a closer look. A much closer look. We're talking about seeing the atomic structure of the flaw itself. Okay, first tool up. Selected Area Electron Diffraction, or SAED. The easiest way to think about this is like material fingerprinting. You shoot a beam of electrons at your sample, and the way they bounce off creates a unique pattern. That pattern is like a fingerprint that reveals the crystal structure. It's how you identify what something is made of at a really fundamental level. And their second tool was even more powerful: high-resolution electron microscopy, or HREM. Now this is like taking an atomic scale photograph. It's amazing. It doesn't just tell you what's there, it shows you how all the individual atoms are arranged. You can literally see the structure with your own eyes. So, armed with these incredible tools, our detectives were finally ready. It was time to unmask the materials hiding inside these strange little flawless flaws. The first fingerprints from the SAED came back and pointed straight to graphite. Now, this wasn't a huge surprise. Remember, the scientists had put carbon into the mix when they were making the material, so finding graphite made sense. So case closed, right? Nope, not even close. Because as they looked closer at those diffraction patterns, they saw these extra little satellite points. Little dots that graphite, all on its own, just couldn't explain. It was a dead giveaway that something else was in there, a hidden accomplice. And this is where that atomic scale photograph, the one from the HRM, became the smoking gun. The researchers could literally see two different patterns, two totally distinct atomic spacings, right there inside the inclusion.
One part was the graphite, sure, but the other was something else entirely.
So they measured those atomic spacings, ran the numbers, and they identified the mystery partner. And it was cubic zirconia. Yeah, a totally unexpected material just coexisting with the graphite inside this tiny little pocket. Wild.
But, like any good detective story, one answer just leads to more questions. Now they knew what was in the flaw, but that just made the mystery even deeper. First, how on earth did these two materials manage to exist together without causing any stress? And maybe even weirder, why were their crystal structures? One is cubic, the other is hexagonal. Why were they so perfectly aligned?
Well, this led the researchers to come up with a really fascinating theory for how this flawless flaw could have even formed in the first place. They called it template nucleation. Okay, so the theory goes like this. It's a three-step process. First, when things are super hot, the carbon separates out while the main structure is still kind of pliable, kind of soft. Then, step 2, as it starts to cool down, the cubic zirconia forms, and it uses that carbon structure as a perfect template. That explains why they're so perfectly aligned. And now, here's the kicker, the solution to the whole mystery. Any stress that builds up is relieved because other elements combine and literally escape as gases. It's like a tiny atomic scale pressure release valve. Pretty clever, right?
Now look, this whole template nucleation idea is a brilliant theory. It really is. But in science, a theory is just a theory until you test it and test it and test it again. So the case, it isn't closed just yet.
So what's next on the to-do list for our science detectives? Well, they need to run a bunch of simulations to see if this formation process is actually the most energy efficient, the most likely path. They've got to verify that those gases can really escape the way they think they do. And maybe most exciting, they're going to run new experiments, tweaking the recipe to see if they can actually control the creation of these flawless flaws on purpose.
And really, this brings us full circle right back to where we started. This whole investigation just goes to show that what we normally think of as a flaw isn't always a weakness. In fact, by understanding and maybe even controlling these tiny, seemingly insignificant details, we might find that they're the real secret to making materials stronger and more resilient than we ever thought possible.
And that leaves us with a really fascinating thought to chew on. We spend so much time striving for perfection, for absolute purity in everything we make. But maybe the real path forward lies in mastering imperfection. Could deliberately engineering these tiny, perfect flaws be the actual key to unlocking the next generation of technology? For space travel, for hypersonic flight, and for things we haven't even dreamed of yet? The investigation is far from over.